This is an introduction to Quadric Surfaces. OpenStax, Calculus Volume 3, Section 2.6. We start by looking at cylinders. We can recognize the equation x squared plus y squared equals 9 as the equation of a circle in the plane. And then sketched in 3 space, we come up with a familiar cylinder. We can look here, x squared plus y squared equals 9, 3x equals 3y equals 0 satisfies the equation, and then setting z equal to 0 still satisfies the equation. Changing that z value to any value that you like will still result in a point satisfying the equation, hence this blue dot, that point. Changing the z value will result in points lying along this vertical line. That vertical line is parallel to the z-axis. This is the notion of a ruling, the vertical line. In general, a cylinder is one where you can produce rulings. Let's look at some examples. Here we are in GeoGebra. In GeoGebra, we have typed in this right side of the equal sign, and then when we hit return, we result in this vector-valued function. This vector-valued function depends on u's and v's. Those are the parameters. The u is taken from negative 2 pi to 2 pi. The parameter v is taken from 0 to 10. These first 3 entries are reproduced here in the vector of u and v. Namely, x is set equal to u, y is set equal to sine of u, and z is set equal to v. Notice that the first 2 equations depend on the same variable u, but the third equation does not have anything to do with u. It is in its own variable. Now, when we have x set equal to u and then y set equal to sine of u, that's essentially the equation y equals sine of x, which is sketched here. We have the x-axis horizontal, the y-axis vertical. We're looking at the sine wave over the interval negative 2 pi up to 2 pi. Let's click on this image and rotate it so that we get a vantage point of the first octant. Like before, we can pick any point on the y equals sine of x sketched in the xy plane, pick any point, and then vary the z coordinate, and we will still have a point which satisfies this equation. That means that we're looking at a vertical line on this surface, resulting in rulings. These rulings are again parallel with the z-axis. Thus, this surface here, the one sketched for y equals sine of x, is in fact a cylinder. Nice. Let's do another example. Same idea. We're in GeoGebra, and we start typing out surface. We enter a parameterization, x equals u, y equals v, z equals u cubed over 50, and then set bounds for u and v. As we have x equaling u and z equaling u cubed over 50, what we are sketching is the surface corresponding to z equals 1 over 50x cubed. Note that this equation does not depend on y. So, looking at this cubic graph, picking a point on the cubic graph, we can vary the y-coordinate and still produce points which satisfy this equation. Hence, in this graph, we get rulings which are parallel to the y-axis. Nice. One more notion, the notion of a trace. We have a surface, we have a plane, we look at the intersection of the two, resulting in a trace. In this book, traces are only done in planes parallel to the coordinate planes. Let's sketch a sphere in GeoGebra. We can type in sphere pass into it a point, which will be the center, and the radius. Alternatively, we could type out this equation. This sphere is centered at the origin and of radius 5. Here's the resulting graph. We're looking from the vantage point of the first octant. Red axis is the x-axis, green axis is the y-axis, and the blue axis is the z-axis. We also have sketched the xy plane such that the intersection is producing a circle of radius 5 in the xy plane. Let's bring in a different plane. For example, the plane x equals 4. This equation x equals 4 does not depend on y or z, so that when we sketch it, we see that it is a plane parallel to the y-z plane. This plane is 4 away from the origin. The sphere contains all points 5 away from the origin. Hence, these two surfaces intersect. Let's ask GeoGebra to sketch their intersection. Here we have the intersection sketched. We see that it is a circle. Nice. The circle is an example of a trace. Here's an assignment for you. Use GeoGebra and sketch these two cylinders. Use the surface call so that your sketches will appear with rulings. Here's a challenge problem. Do the same thing for this surface. In italics, I've typed out that you may need to sketch the surface in 2 pieces. Other than that, it is not much of a challenge, but see if you can do it. Excellent. Let's go ahead and dive into quadric surfaces. We're looking at an equation. The equation's been set equal to 0. On the left-hand side are variables x, y, and z, and the highest power is 2. Thus, a quadric surface is the graph of a degree 2 polynomial equation in x's, y's, and z's. An example is an ellipsoid. If the denominators on the left-hand side were all the same number, the ellipsoid would be a sphere. By varying the denominators, we morph the sphere. To see how the sphere morphs, let's go ahead and consider traces. In the equation, I've gone ahead and I've covered up the x term. Here I have graphed in the yz plane an ellipse. The yz plane is also given by the equation x equals 0. In this equation of the ellipsoid, setting x equal to 0 is essentially covering up that term. Looking at this particular ellipse, which is the trace of this ellipsoid, we can look at the y-intercepts at y equaling 4 and y equaling -4. And then z would be 0 at those 2 points, z equals 0, and y equaling ±4 satisfies the equation. Repeat, covering up y. In other words, y equals 0, that's the xz plane. We result in another ellipse. Here on the horizontal axis, the intercepts are at different values. So while it is an ellipse, it takes a different form, a different shape. And one more. Here is the trace of this ellipsoid in the xy plane, namely z is 0. Good. Have GeoGebra sketch the ellipsoid. And here I've done it such that the 3 traces are also included to give these shape. Excellent. Let's do one more example of a quadric surface. The previous quadric surface was an ellipsoid. The name made sense because all three traces were ellipses. Here, the name of this quadric surface is an elliptic paraboloid. Let's consider traces. Horizontal traces result in ellipses. Here, I've sketched in z equals c to identify an ellipse. This ellipse may take the form of x squared over some number plus y squared over some number equals some constant. Nice, that's a horizontal trace and ellipse. Place that to the side, and next let's consider vertical traces. We can consider a vertical trace x equals d, like we have pictured here, parallel to the yz plane, or we can consider a vertical trace parallel to the xz plane. Either will result in a parabola. Nice. This parabola might take the form of some number plus, so this some number is, we're letting x equal d, plug that into this form, get some number, call it a prime, leave the y squared over b squared, and then on the right-hand side, replace that with z over c. If you look at this parabola, as we vary y, we produce different values of c. This constant a prime would have to deal with the height of the vertex. Nice. So this particular elliptic paraboloid has the z-axis as the axis of symmetry, and the z variable is isolated, appears linear. The z variable is set equal to a sum of quadratic terms. Thus, this z variable cannot be negative, assuming that c is positive. And note that the graph does not appear for negative z's. Likewise, if we were to have an elliptic paraboloid given by this second equation where the x is appearing linearly, then this elliptic paraboloid would have an axis of symmetry as the x-axis. Nice. Let's go ahead and summarize our quadric surfaces. There are a total of 6 that you want to know. Here are the first 3. We have already looked at the ellipsoid. Note that in this equation, we have it set equal to 1, and the remaining 2 equations are also set equal to 1. Something else to notice is that the 3 surfaces share in the fact that they do not contain the origin. And that can be attributed to the equations being set equal to a non-zero constant, 1. Let's go ahead and look at the traces. We know on the ellipsoid, all 3 traces are ellipses. If we take the equation of the ellipsoid and we swap out one of the plus signs with a minus sign, we get a hyperboloid of one sheet. Horizontal traces are ellipses. Vertical traces are hyperbolas. The axis of symmetry on a hyperboloid of one sheet corresponds with the variable on which you've introduced a minus sign. Nice. Now, to go from a hyperboloid of one sheet to a hyperboloid of 2 sheets requires 2 minus signs. The variable on which the plus sign occurs corresponds with the axis of symmetry. These 2, hyperboloid of 1 sheet, hyperboloid of 2 sheets, have horizontal traces, ellipses, vertical traces, hyperbolas. Nice. And here's an assignment. Sketch this quadric surface, identify what it is, and then use GeoGebra to also sketch out 2 representative traces. That was 3 of the 6 quadric surfaces. Let's look at the remaining 3. Note that in this first equation, it is being set equal to 0. Look at the remaining 2 equations. Note that moving the left z to the right, we can result in an equation set equal to 0. All 3 of these equations can be set equal to 0. All 3 of these surfaces contain the origin. The previous 3, none of them contained the origin. The previous, they could all be set equal to a constant. Good. Here on the elliptic cone, the variable, everything is quadratic. The variable with the minus sign corresponds with the axis of symmetry. In the elliptic cone, horizontal traces are ellipses, vertical traces are hyperbolas. Note, in the elliptic cone, all of the variables appear quadratic, degree 2. The remaining 2, the elliptic paraboloid, has a variable isolated and appearing linearly. We've seen this one earlier. The variable that's isolated corresponds with the axis of symmetry. And this one is set equal to a sum of squares and thus cannot be negative. Versus the hyperbolic paraboloid is set equal to a difference of squares, and thus the isolated variable can be any real value. On both the elliptic paraboloid and the hyperbolic paraboloid, vertical traces are parabolas. The elliptic paraboloid, horizontal traces are ellipses. Horizontal traces on the hyperbolic paraboloid are hyperbolas. The vertical trace parallel to the YZ plane is a parabola opening down. The vertical trace in a plane parallel to the XZ plane is a parabola opening up. Nice. Another assignment. Another quadric surface for you to identify, sketch, and this time produce 3 representative traces. That was a quick introduction to quadric surfaces.